Last time we started working on section with 3.4 on properties of logarithms, and we look at this madness here, right? That's how we wrap up last time's lecture, in which we pretty much put together all properties of logarithm in the same exercise, which is something we would expect to do. We would be expected to do on an exam, on a homework, etc. Right? Okay. So what we did last time is to expand a compressed expression and turn it into a sum or difference of different logarithms. And trust me, guys, if this looks madness, which it is actually, this is to later simplify a lot of the work when we do calculus involving logarithmic functions, rather than, well, for those of you who may have taken calculus, rather than doing a huge chain rule with quotients and product, no, we expand it into many terms, and it's better to do the calculus on simpler functions rather than that madness. Well, you'll see when you get to 150, or again, if you have taking calculus before, I guess you can relate to that, to what I'm talking about. All right, so now we're going to do the backwards process. In some cases, we need to compress logarithmic expressions to write them into one. We will see later under which situations we do one and under what other situations we do the other. And well, so we're going to use these properties of logarithms. So for example, if we have a sum of two logarithms, we will write it as one single logarithm, and the argument will be comprised by a product. If we have a difference of logarithms, write it as a single logarithm, but in this case the argument will be comprised by a quotient between the two arguments. And last but not least, might remember that SmackDown basketball rule. Well, for the expansion we did the SmackDown. Now we're going to do the reverse. We're going to do the basketball property. You'll see how it works this time. So let's have a look at this first example. Letter A. That's 3 logarithm base 4 of y plus 5 logarithm log base 4 of z and minus 7 log base 4 of x. Well, first things first, in order to use the product rule and the quotient rule, and let me go back to the first page of this. Notice in these properties, notice how we have ones as coefficients, right? We don't have anything else multiplying, so whenever we don't have any coefficient, it's supposed to be understood to be a 1 or nothing else. Well, so here for these 3 terms right here, we have coefficients in front of the log operator. Well, we need to get rid of those coefficients. How about we send them to become an exponent by the basketball rule? All right, so let's basketball all the coefficients. However, I notice there's one negative term. Keep the negative term. I know you might be thinking, well, should we do it with the negative sign, including the negative sign? Well, that's another way, and actually I will spend a couple minutes doing it that way as well. So you can see it's the same thing. I'll show you in a minute. In the meantime, let me do it just by basketballing with positive exponents, but leaving this negative, the negative sign. Well, so this will become the following. So this will be log base 4 of y plus log base 4 of z, or y to the 3rd power rather, that's the exponent, and 5, and minus log base 4 of x to the 7th power. All right? So only then we may be allowed to use compression rules. That is to write this sum as a product, and well, you'll see what we're going to get here. So that's number 1. Log Base 4, well, in this case, we have an addition. That addition of two logarithms becomes one single log. However, let me open parentheses and write down the product of these two arguments here. That is y cubed times z to the fifth. And I know there's a minus term that we could have written down in the denominator. We could, I mean, after getting some practice, you could do this in your head. I mean, it just becomes a second nature. But in the meantime, I'd rather do like one property at a time. Okay, so that's minus log base 4 of x to the 7. Okay, so what do we have overall now? We have a difference between two logarithms. So in accordance with the quotient rule, so we're going to use the quotient backwards. So by having this difference, I'm going to write log base 4 parentheses y to the third power z to the fifth power over x to the seventh power, and now we have one single logarithm. All right? So that's how it works backwards. So back then, the product was turned into a sum. The quotient was turned into a difference, and the power went to the front as a coefficient by the smackdown rule. Now in the reverse process, the coefficient becomes back again an exponent by the basketball rule. The addition becomes a multiplication, and the subtraction or the difference becomes a quotient by looking at these same rules, but this time in a backwards fashion. All right. Okay. What's the other way? Let me. I think it's worth looking at it, because in the end, well, you get to choose how to do this. I mean, as long as you don't make up your own rules, of course. So let me write this down. Let me write it here. Then I'm going to erase it because I'm going to need the space for the second example. So if you printed this, just use the back side of the page or something. So 3 log base 4 of y plus 5 log base 4 of z minus 7 log base 4 of x. So this will be, well, number 1, again, by basketball rule, power, and in this case, as opposed to what I did in the first way, I'm going to send the 7 along with its negative sign. All right, so that's going to be log base 4 of y to the third power plus 5, no more 5 log base 4 of z to the fifth power. And then, well, since I'm carrying the negative to the power, we should write this as positive. Okay, plus log base 4 of x to the negative 7. And then what do we have here? We have an addition of 3 logarithms. So we can write this as one single log base 4 of y cubed z to the fifth x to the negative 7. But I mean, we don't like negative exponents. How about we send that factor to the denominator? And surprise, it's the same, isn't it? It's the same thing. So how do you want to do it? It's up to you. My personal advice, of course, is to keep the term negative. Just carry the exponent as positive, and in the end, just use the subtraction quotient rule, the difference quotient rule. You know. So, but again, if you feel more comfortable doing it this way, that's fine. That's fine as well. All right. Okay, I'm going to erase this part right here. Ultimately, it's recorded, so you can refer to it, because I need the space for the next example. And well, I guess the first example is kind of the straightforward type of example, kind of the cheesy example. But well, let's do something more elaborate here with more potential pitfalls here. And well, one of the potential pitfalls for logarithms is to notice how all these terms are all over the place. What do I mean by all over the place? Well, in terms of their signs. So we have a positive, a negative, then a positive, and then a negative. So they're all over the place here. It's not like in the previous example we had the first two to be positive. We compressed them as a product, and then we took care of the difference to turn it into a quotient. So whenever you see a madness like this one with terms having the signs like all over the place, my advice is to, okay, let me highlight the positives. Highlight the positives, and let me highlight the negatives. Negatives with negatives, positives with positives. All right, and I'm going to rewrite the order of the terms. I'm going to write the positives first. So that is 3 ln of x plus 1/2 ln of x squared plus 25. And then let's start now writing the negatives. Minus ln of 9. And what else? And minus 2 ln of x minus 4. All right? And let's see. So this is what we're going to do. So we can already use the basketball rule. However, before using the basketball rule, how about, well, there is a purpose actually of writing the positives first and then the negatives. And that's so we can easily see that the last two terms have a greatest common factor. And that greatest common factor is going to be the negative sign. So, okay, let me rewrite without doing any basketball. I know we can already do it. 3 ln of x plus 1/2 ln of x squared plus 25. Minus, and I'm going to open brackets to write down ln of 9, plus, all right, plus ln of, no, not just ln, that's 2 ln of x minus 4, and close the brackets. All right, only then, well, why not? Let's basketball the coefficients and turn them into exponents. That is, make the 3 become the power, make the 1/2 become the power. And careful when we have more than one term. For like the case in the second logarithm, we have a sum of terms. That power will affect both terms, so not one term at a time, okay? So careful with that. Well, over here, the ln of 9 doesn't have a well, it has one, but that coefficient is an invisible one. And well, I'm not going to do basketball on these ones because, well, I think I did the basketball in the wrong place. And that is here and here. I mean, it's kind of silly to send the 1 to become the power of 1. It already is, right? So we don't need to do that. Well, what about the coefficient of 2 here? Well, let's do basketball on that one. So that's going to give us 3 ln of x cubed plus ln of x squared plus 25 to the 1/2 minus bracket ln of 9 plus ln of x minus 4 quantity squared. All right? So it looks like we're getting somewhere because we no longer have coefficients in front of logarithms. And as soon as we see each individual logarithmic term, it looks like we can already use the other properties, the product rule, backwards product rule, because we have an addition, use it backwards. And well, I think that's something we should do now. Well, addition means one single log of a product between these two. That's ln of x cubed times x squared plus 25 to the 1/2. And I know what you might be thinking here. That 1/2 power, it's the same as saying square root, which we will do. But rather do one step at a time. We'll do that in the next step, actually. And then that's a minus, and this will be ln overall of 9 times x minus 4 quantity squared. All right. So that's a product because, well, we have an addition symbol. The addition of two logarithms is the logarithm of the product of the two arguments. And well, overall, we have a difference between two logs. So see how every time we see less and lesser ln symbols until we reach to one single ln symbol. All right, that being said, let's go ahead and use, in this case, the difference to become a quotient. In this case, keep in mind that order matters in a difference or a quotient, right? So the first one goes in the numerator, and the second one is going to go to the denominator. That is one single logarithm, ln, of x cubed, parentheses, x squared plus plus 25 to the 1/2 power, and over 9 x minus 4 to the second power. And we are essentially done with this. However, how about we rewrite this 1/2 power as a radical? I mean, we could have done it in this same step. I mean, it's valid. It's not like we would be deducted 1 point for missing that step. But I'm trying to be as explicit as possible when showing the steps here. So, and that's simply going to be bracket x cubed square root of x squared plus 25 divided by 9 x minus 4 quantity squared. And that's final answer for this one. And again, my advice here is if necessary, if you think it's necessary, rewrite the whole humongous mess here by having the positive terms first and then the negative terms. So.
Can we still add the 1/2? To the 25?
This one?
Yeah.
Well, this one is a power. So whenever we have a rational power, say, for example, x to the m over n, this is the same as saying the nth root of x to the m. So essentially, the denominator of the rational exponent is going to tell us the index of the radical. So for example, in this case, a 1/2. So it would have been something like this. This quantity raised to the first power, and the index is 2. But on the one hand, we don't need to write power 1 for anything. And when it comes to radicals, we don't need to write the 2. Whenever we see the radical symbol, it's always understood to be square root, unless it's a cube root, 4 root, 5th root, etc. We would see this number explicitly, the number 3, number 4, number 5, and so on and so forth. And careful because, and I think it would be worth to talk about this, the square root of x squared plus 25. Is that the same as the square root of x squared plus the square root of 25, which is x plus 5? Is that yes or no?
Doesn't it have to be like 25x squared for you to do that?
25x squared.
Like square root of 25x squared.
Of 25x squared or 5 squared, because since it's square root, yes, no need to do this. So I'm essentially distributing the radical of over the sum. So be careful with this, because this is one of the most common mistakes in algebra. Another mistake here is x minus 4. That's x squared. X squared minus 4 squared equals x squared minus 16. No, this is not correct. In fact, we have to write that x minus 4 squared as the product of x minus 4 in itself and then do the foiling. So careful. And for the case of the radical, so suppose we have square root of, okay, let me do that in general again, a squared plus b squared, or you know what, simply ab. Don't have to be squares. Square root of a plus square root of b. Okay, try some numbers, and I'm going to try the number, okay, some numbers that are perfect squares. A equals 25 and b equals 9. How about that? So the square root of 25 plus the square root of 9, and then the square root of 25 plus 9. So the square root of 25, which is 5, plus the square root of 9, which is 3, that equals to 8. But 25 plus 9, I believe that's 34, isn't it? Is the square root of 34 equal to 8? No, right? So careful when dealing with radical expressions or binomials, trinomials, polynomials raised to powers, regardless of the power. No, we don't just distribute the power. We don't distribute the, what's it called, the radical, or even for logarithm, we don't distribute the logarithm for a sum or difference of terms. Okay, I'm going to leave this just so when you look at the video, I mean, it looks like a reminder of what it's not to do. Yes?
So on the test, we shouldn't try to distribute?
No, just leave it like this. That's correct. Yeah. Okay. But oh yes, evaluating logarithms whose base are not neither 10 nor e. Well, I believe we already talked about this, when it comes to the graphing calculator, when we want to compute, logarithms of certain numbers. Let me quit here, let me clear all this, and clear history. Okay, so our graphing calculator, as most calculators, especially the older versions of the graphing calculator, are equipped to evaluate logarithms base 10, which is this log here, right here, and ln, which is logarithm base e. So all our calculators evaluate ln's and logs. However, what if we wanted to evaluate, say, logarithm base 7 of 5? Well, we cannot. Some calculators cannot do it. Well, actually, the newer calculators can. So all you do, if you have like some of the newest models of this graphing calculator, in this case, that's the CE, the Color Edition Plus. All you do is go Math, and for, I believe it's under Num. Let's go up a few. No, it's not under Num. It's under Math, actually. Go up, and we will have that log base function here. And all you do is simply evaluate, say, log base 7 of 5. Whoops. Log base 7 of 5. And it's simply going to give us the answer. All right? However, not all calculators are equipped with this function in our graphing calculator. So how do we do? And well, I mean, of course, if you're working on your homework, you can Google logarithmic calculator and the like, However, on the exam, you might be asked to evaluate, or well, if you're not allowed to use a calculator on the exam, you may be asked to at least express this logarithm in a way that we can evaluate, and that is as a log base 10 or log base e, which is the natural log. Well, now, in order to do this, we need what we call the change of base formula. So we need to change the base. Instead of keep working with base 7, change to another base. And you can change to your favorite base. Even if you want to express, some logarithm base 5, but you want to express it as a logarithm base 37, if you will. That's fine, you can do it, and it may be required if we are working on another problem that requires it to combine logarithms that are base 37 and we're given logs base 5. However, for now and for the sake of simplicity, what we're going to do is transform logarithms base b, where b is a base other than 10 and e, and all we do is write the quotient of two logs. Careful, because this is not the logarithm of a quotient, this is the quotient of two logarithms, two totally different things here. And well, so we get rid of the base, the base that we can't evaluate on the calculator, and let's write this as a logarithm of x over logarithm of the older base. And notice the subscript here. Invisible subscript, that's log base 10. Invisible subscript, that's base 10 as well. And we can do it the same way with ln if we will. All right? So let's use a change of base formula to evaluate log of 13 on the base 9. So all we do is write down the ratio of two logarithms here. And so that's log over log. So the argument in the numerator is going to be the original argument, which is 13, and the argument in the denominator is going to be the old base. Okay? Let's see what we get. Let's go to the graphing calculator, and I'm going to show you the two calculations with the older base, with the new base, and we can come up with another base if we will. So we don't have to turn this into log base 10 if we want. We could have also done the following. Check this out. ln of 13 over ln of 9. Either one, it's your choice, that's fine. I'm going to do all calculations here. So number one, okay, log, okay, let me clear all this. So that's log of 13, close parentheses, and divide that by log of 9. And what's that? 1.1674. We're going to round this to 4 decimal places. So usually for logarithms and exponentials, the rounding rule is 4 decimal places. So 1674. So this is approximately 1.1674. Okay, I did it via the log. Did I do the ln or the log? Okay, log. I'm going to repeat the calculation on a different base. That is, as a base e using natural logs. So let me clear this. I'm going to do ln of 13, close parentheses, divide that by ln of 9. Same answer. Same answer. Now, if you manage to find a utility to evaluate logarithms of the given weird base, well, like this calculator, for example, let me do it. Math log base, and I'm going to do log base 9 of the number 13. Same number, right? But again, the reason why we stop and look at this change of base formula, it's because later we are going to apply this formula to solve other kinds of problems, to even solve equations, and well, you'll see what I'm talking about. Okay, so actually in the next set of exercises, that's where we will need them. All right. That being said, how about we evaluate this logarithm? So it's a logarithm of the square root of 7 on the base square root of 3. I know the bases are so weird. But again, we can either evaluate this as log of the square root of 7 over log of the square root of 3, which is the same as saying log of the square root of, oh no, not log, actually ln, the square root of 7, ln of the square root of 3. Can we rewrite this as a quotient of two logarithms or even another base? Of course, you can use your favorite base. These are base 10. These two are base e. But we can also convert this into, I don't know, maybe log base 19 of square root of 7 over log base 19 of root of 3, or even better, maybe log of square root of 7 base 23 over log base 23 of root of 3 rather. You can choose your favorite base to convert into a newer base. However, we take advantage of this property to evaluate via calculator, which in most of the cases, it's equipped with log base 10 and ln's, right? So, but if you compute all these four, you should get the same result. But I'm going to compute only one for this one. So I'm going to do the ln. I'm going to do ln. So ln of the square root, where's the square root here, of 7, and make sure to get out of the, oh, that's not, let me delete, get out of the radical, close parentheses, divide by ln of the square root of 3, get out of the radical, close parentheses, and enter. So that's 1.7712. Well, we're going to keep it at 12 because the next digit is a 4, and it's not good enough to round up that 2 to 3. 1.7712. All right. Okay, so now that we have pretty much all properties of logarithms together, let's evaluate expressions involving these logarithms, in which, well, we already did some of them, like the inverses, finding logarithm of 1, which is 0. We did those in the previous section. Now we're going to combine pretty much all of them. And now let's have a look at the first one. So what do we have? We have logarithm base 6 of 9 plus logarithm base 6 of 4. So in this case, we have an addition of two logarithms. And well, we can combine these two logarithms together because they are like terms. What do I mean by like terms? So logarithms are like terms if they have the same base. Okay? So for example, in this case, they have the same base. We can use the addition to product. And that's going to be logarithm base 6 of 9 times 4. All right? And of course, the goal here is to simplify these logarithms without the use of the graphing calculator, just by using the properties. All right? So 9 times 4, that equals 36 on the base 6. And well, this problem right here, logarithm of 36 on the base 6, we can simplify this well. At the beginning of the logarithms chapter, we went back and forth between exponential and logarithm. So essentially, the result will be the exponent or the power we need to raise the base so that we get the argument, right? So in other words, what power of 6 equals 36? So that's how we did it back when we did the exponential form. But again, like I mentioned a couple of lectures ago, we don't need to keep going back and forth between exponential and logarithm. So we will use properties. In other words, our goal is to rewrite this number 36 as a power of 6, which is quite possible. That's log base 6 of 6 to the second power. And the idea here is to find the match between the base here, or the argument, and the base of the logarithmic function. That is, log base 6 cancels the 6, and final answer, which is the same result that we would have obtained if we went back and forth between exponential and logarithm. All right, so what's next? What time is it? All right, we have time. Okay, what do we have over here? So we have an exponential function with two logarithmic terms in its exponent. So that's 5 raised to the logarithm base 5 of 6 plus log base 5 of 7. Well, I know what you might be thinking. Should we just cancel? Because check this out. The base of the logarithm of both logarithms here match with the base of the exponential, isn't it? So might as well, why not? Hey, cancel, 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 cancel. No, that's not how we cancel this. In order to cancel this, we need to combine the logarithm together into one single expression. And well, what do we have? In the exponent of the 5, we have an addition of two logarithms. And we're going to write it as a single log by combining them together using the addition to product property. That is 5 log base 5 of 6 times 7, okay, which is 5 raised to the log base 5 of 42. Well, in this case, since we have one single logarithm and one single base, cancel log base 5 with the 5, the exponential 5. Final answer, the number 42. Okay. Now, as a side note, okay, so for the last, I don't want to go through the next examples because they may take a good minute to go. In fact, these are going to get weird, and well, I don't want to rush through the weird ones. I'd rather start fresh on those next time. But I would like to write a side note here before we go. So, and I'm going to relate it to example letter A. So, for example, if we had something like log base 6 of 9 plus log base, 5 of 4, these two logarithms cannot be combined. And the reason to that is so this will be equal to itself, log base 6 of 9 plus log base 5 of 4. And as a side note here, cannot combine since the bases, that is, these subscripts right here, do not match. All right? Whoops. Come on. Do not match. All right? That's why.